Thanks for the warm welcome, I guess. Well, that's very nice. So, as already said, today I get to talk about something that I personally deeply care about. The transition from narrow artificial intelligence, like you hear in most use cases today, to artificial general intelligence. A system that's capable to solve any problem without being reprogrammed better than a human, which is the ultimate goal that artificial intelligence had when it was first presented decades ago. So this is what I'm going to try to do today. But before we get into the cutting-edge, high-level ideas of today's research, let me quickly get into deep neural networks. You've all heard this buzzword. It's used in almost every application today. But honestly, the concept behind it is very simple, and for that very simple complex, it's extremely powerful, and I think it's important to understand that. This picture is probably nothing new to most of you. You get some inputs, you have this neural network, you get some prediction. But honestly, it's really nothing complicated. You get numbers as an input, numbers as an output. These white little connections between the neurons are also just floating point numbers. These are actually what's learned, what's changed in a neural network. That's what you do when you train on a data set. You change these weights to successfully map from inputs to the correct outputs. That's basically what you do with a neural network. The nodes, these neurons, are where all the computational magic happens. Or it's not really magic, because all it is you sum up the neurons from the previous layer, multiplied by their weight, throw that through the function you see on the on the right of the screen, and that's the value of this neuron. And honestly, that's essentially the basic computation that happens in your vanilla neural network. That's it. You learn from something we call data. Data is nothing but the pair of inputs and outputs, or labels. These inputs get fed into the randomly initialized, or kind of randomly initialized, neural network. Out you get some garbage prediction, because, well, with random weights, you'll probably not have a very successful neural network. Then you get your labels. You use what you know about the data, compare that to the prediction, which this comparison yields some difference. You could really view it as the difference between prediction and labels. And you get that loss, this difference. What you now try to do is you take that loss, you take the weight, and you minimize the loss by changing the weights. Congrats, you just understood what neural networks do. Really. It's not that difficult. Okay, and now introducing you to the mathematical wording of things, you calculate the gradient of the loss with respect to the weights. So it's even that is pretty understandable, I think. That's just, for people who understand that, infinite chain rule. Or not infinite, but almost. So that's the basic neural network. Now you can do some fancy things by wiring things differently. You could, for example, feed the prediction that you made on the input back into the input and the next time. That's how you do time series analysis. That's how you analyze language and things like that. Recurrent neural networks. Well, suddenly it's not that complex anymore, right? You do that a couple times for for every word, for example, you input one word at a time and the state that was computed the last time, and well, you have something that analyzes language. Convolutional neural networks. While this architecture is a bit harder to visualize simply, essentially what it does is it tries to exploit and extract the hierarchical information you have in an image. You have low-level edges, then you have mid-level features, and you have high-level features like noses and faces and things like that. Out comes a probability, in case you're doing classification on images, out comes a probability of certain classes. So those are two very famous, very widely used neural network architectures, which are basically if anyone sells you a neural network, or I do, that's what you get, and some things around it. Well, so in other words, because I like to frame things simply, having different neural network architectures just means wiring the neurons differently and maybe having some fancy layers in between, like batch normalization and things like that. There are, of course, improvements that I didn't show, this is not all of it, but this is the simple way to explain neural networks, and really, honestly, if you get that, you get the essence of it. So if we take this knowledge, we understand we're mapping inputs to outputs. That's a function approximation. You're approximating a function that takes in inputs and gets outputs. This is a numerical optimization problem, something that we in computer science and mathematics know how to deal with very well. If we have computational power, And in this case, if we have data. And, well, turns out we have both of that now. Neural networks are a very old idea. We didn't have that back then. We have it now. That's why they are so famous right now and why there is so much work done and research done in the field, because we can experiment with this technology today. What neural networks do is, in their limited number of weights, they try to extract patterns out of the data you give it. Because, well, your data usually has hundreds of gigabytes if you have a big data set, but your neural network weights don't. They have less possibility to save things, but they still have to approximate the relationship. So what they do is they try to compress the information inherently by optimizing this, by minimizing the loss, and they understand sort of the patterns in the neural network. And this generalizes, due to the pattern recognition, to unseen examples. So, yeah, well, that's supervised learning in a nutshell, but that's not human learning in a nutshell. Humans have various different ways to learn, and that leads me to where I want to get with this talk. What we do is, we always have the same outputs. We have muscle movements, like everything I do right now is nothing but a muscle movement, even my speech. Everything else is nothing but a muscle movement. You play chess, well, you move your hand, there's nothing else. You always get the same sensory input format. You get your eyes, like what you feel, what you smell, things like that. Always the same dimensionality, no matter what you do. The human brain is the black box that handles that. The human brain performs exploration by trying things. For example, I could run against this wall and see if you guys like that. Probably not. Like imitation, that's what I do in school, or should, at least. Explanation, explanation is what I should do in school. Imitation is what children do with their parents. Like that's the fundamental way we learn. We have different strategies for that. Also, we're capable of abstracting between domains. For example, if I'd learn like how to jump, I'd probably get better at learning how to run, things like that. And we are also able to decide how we want to learn something. We are capable of understanding different ways of learning, like imitation, exploration. Like we can decide how we want to approach a concept. For example, it's pretty hard to learn to play chess perfectly just by exploration. You're just going to have to play way too many games. There you go, that's a problem that we'll face later with artificial general intelligence. So, but first of all, let's try to give AI the same framework to learn in that we've just had for humans. Looks pretty similar, that's good. We have an environment, could be a game like Go and chess. You've probably heard of Go and chess bots. That returns an observation, which could be a snapshot of the board. A reward, well, for example, it could be 1 if you win, 0 if the game is still going on, and -1 if you just lost. The agent is where the AI is at. That's where the algorithm is. That's what learns, so that's like basically the substitution for the human. And the action in an environment like chess would be move piece X from A to B, whatever, things like that. The difference between reinforcement learning, which is what this framework is called like, it's not an algorithm, it's a framework for algorithms to learn in. The difference between that and supervised learning is, with supervised learning you get a data set and you want to approximate that. With reinforcement learning, you build your data set by interacting with the environment. That's the only thing we do. That's what we do when we live. That's what we do when we learn, and so that's kind of what we want to do with AI to like get to AGI. Which is the short term for artificial general intelligence, of course. So, what does RL do? RL tries some things, sees how good they were, learns from that, and tries to do more of the things that were good. Pretty much exploration. There is, of course, also imitation in that, and you could do many things, but exploration is what it mainly profits from today. Modern AI RL algorithms, and don't worry, I'm not going to go into each of them, are very good. There is a lot of development in this, especially in the last 2 years. There were so many advances that like just go unnoticed because they happen so fast. But one thing to note about them is that all of them, deep learning. So that's why I like started with deep learning, just to make sure you understand that like the heart of this whole thing isn't that complex, but that's what pushes the state of the art, that we are able to use this powerful function approximation and build algorithms around it. That's basically what reinforcement learning algorithms are. So success stories of reinforcement learning, you've all heard of AlphaGo, I'm sure, or at least most of you. AlphaGo is a program by Go that learns to play this game called Go, which is extremely complex, has an insane amount of game states, and was something, and that's an important point, that people thought, 10 years ago at least, is something that only artificial general intelligence could play. That was sort of a benchmark for them. That was like, if there is ever a program that can play that, we have artificial general intelligence. Well, turns out no, we don't. But that also raises another question, and especially like me working in research, it's important to know where you are. So where is the border? I'd like to have some metrics. I'd really like to know when I can call something AGI. Well, there is this Turing-Test thing that many people seem to like, but first of all, the Turing-Test was already solved and we don't have AGI, so well, no. But let me tell you why. The Turing-Test consists of a human asking, like, a question, I guess, and getting an answer. It doesn't know whether the answer comes from another human or comes from a computer. If the answer comes from, if he can't tell the difference after asking like a number of questions, the AI won. The AI is now like won the Turing test. So that actually motivates the AI to act like a human, which, well, in this case, in the simple question, equals thinking intelligently. But if we say in the same domain of math, well, we'd want our AI to be able to answer something like this. But most humans wouldn't be able to. So again, bad metric in my opinion. Honestly, like, it's just, like, that's not a good metric. But Alan Turing is a nice guy, like a really awesome person. Don't get me wrong, like great person, yeah. But another one, very human thing, is humor. And humor is so complex, like it's just, look at this image. Like for you, instantly, you get it. Obama does something funny, people in the background laugh because like this guy thinks he weighs more than he actually does, but well, in fact, AI would just classify this as like group of persons standing in a floorway or things like that. So that's the state of the art in terms of computer vision. That it doesn't understand this, and that's something that I personally and some other researchers do think could be a good metric for AGI. And of course, the obvious metric is that it's just one algorithm that can solve all problems without any changes applied to it. Like that's of course a criteria to be fulfilled. But to build AGI, it might be useful to look at GI, which we have in our brains. So let's just do that. How do we solve problems? Imagine we have a wall in between us and a goal. And we're thinking about like, could I run through that wall? Or no, bad, because like we already tried that and that hurt. So maybe let's try climbing. We already tried that. We didn't get high enough. So what we're doing is we're using a reservoir of memories of experiences of the same domain and think, have we done that? Has that worked? Let's do that again or not? So that's something we do. We have general memories that we can adapt and use in any domain. If there was not something like we already experienced this exact problem, we might combine solutions from different domains, like, oh, I know what a ladder is. That thing helps me climb. Let's do that. So then, what we'd do is we'd plan a macro strategy. We'd think like, I could do this step, then this step, then this step. Then I'd jump down, that hurts a bit, but no, it doesn't matter, I'm at the goal. So that's what we'd do next. And note that, I said before, the output is always muscle movements. But we are able to plan on a macro scale. We don't plan like every single movement we do, which is important. Because on the next thing, when we execute our macro plan, we intuitively know how to execute each micro action on the way, each little muscle movement, each little step. We understand that, and we learn to improve our micro actions while we execute them, no matter what the macro problem is. Doesn't matter whether you climb a wall or whether you walk, whatever. You improve your physical micro actions. And we also have an intuitive understanding of physics because of that. Otherwise, I'd just fall over right now. Yeah. And the next thing is we are adaptable. If the ladder suddenly decided to break, we'd be able to like find a new plan. We'd not just like blindly follow what we've thought of before and then fall down. We'd just think like, oh, what can I do now? And we'd do that. So that's something what we would actually like to see in reinforcement learning systems. Because imagine you play not just Go, but like a really complex game where you have to play for like 30 minutes and in real-time strategy action thingies like StarCraft or whatever. That's something that would be really nice. So can our agents do that? What do you think? That's the answer, sort of. Like kind of, actually, like really kind of. It's not that we are at zero, and that's one of my key messages today. It's not that AI is stupid and can't do anything. Like actually, sort of, but not as nicely as we wish. There are some downsides, and that's what this major part of the talk will be about. So what our algorithms are really good at is learning one well-defined task given a perfect simulator, meaning like a Go bot would be able to interact with a Go simulator 1,000,000 times, and that would never be random. That would always work. The rules are programmed into the simulator, and you can learn from that. Obviously, you need an environment, like that's the whole environment part. So that's understandable. We don't need to deal with that. A problem is large amounts of data and trials. If we imagine a robot trying to learn to walk, it's pretty expensive to have a robot try that 1 million times, usually. So that's something that should be fixed, and it's kind of getting fixed by training and simulation and then fine-tuning on the real robot, but there is still a lot of work to do. And the big problem is that this doesn't work with prior information. This whole thing of learning micro-actions that are useful for other tasks doesn't work as well as it does with us humans. But more on that. More on that soon. The near future to-do list for AGI, so kind of what researchers are working on right now and will be working on within the next few months, because honestly, everything after that is completely unpredictable, no matter what everyone tells you or anyone tells you. The first 2 challenges would be this whole transfer learning and hierarchical learning of concepts and things in general. You remember I showed you convolutional neural networks, and I told you that they inherently have this ability to extract hierarchical information of images. Well, what this looks like is like this. The early layers would have small edges and dots as their filter maps. I'm sorry, I can't explain the whole convolutional architecture now. That would take too long. But just stick with the analogy. The early layers have encode these edges and dots. The mid-level layers encode the mid-level features, and the high-level layers encode the high-level features, like faces and so on. And you see there are more of the high-level layers because there are more high-level things than there are low-level things. And that's something we want to use because we don't want to relearn the low-level things for every high-level object. That's an important idea because, well, transfer learning, imagine you'd have a huge data set of images with 3,000 classes of a diverse range of objects. And what you'd now do is you'd gather $50,000, hire a person with a supercomputer, and train a large neural network on that. And boom, you have a great image classifier that's capable of having a perfectly wide and diverse and complete understanding of low-level and mid-level features, but it only knows the high-level features of your specific data set. What you'd want to do is, if you have another data set that you actually care about objects that are not in the main data set, what you'd want to do is, you'd want this big network to somehow add that to its repository of knowledge and reuse the low-level things. And turns out, it's actually very easy. What you do is, you take the high-level layers, train them again while you freeze the low-level and mid-level feature layers, retrain them on the small data set, only requires 100, 200, 300 images, depending on the number of classes per class, and that works. That's great. That's something that many applications of computer vision today profit from. Transfer learning and reinforcement learning? Well, raises the question, hierarchy in reinforcement learning. Again, that's only possible because of the hierarchical representation of things. Yes, actually, yes. In the beginning of 2018, another guy pretty much like me, called a high school student, published a paper. Can I play it like that? Yes. Published a paper where he did exactly that, but only in a very limited domain. This is a great proof that this could work. It's not finished, but what this essentially does is it tries to efficiently solve new mazes without having to learn each muscle movement every time for a new maze. It trains on a set of 10 or 20 mazes to learn the basic movements, and then can be executed on every new kind of maze. So this whole algorithm is built on the idea that you have one master policy deciding which of a given number of sub-policies gets to act now. So imagine sub-policy 1 learns to walk down, sub-policy 2 learns to walk right, sub-policy 3 learns to walk up, and I have no idea why he only has 3 on that 4, but okay, that's the paper. So what this would do then, the master policy would learn, oh, okay, in this part of the maze, I want to work forward. It doesn't have to care about the single muscle movements. Sub-policy 1 does that for it. And that kind of works, actually. That works. If you train that on 10 or 20 mazes, it works. You just train a new master policy for a given new maze, and you reuse sub-policies. That's great. But unfortunately, it's not as cool as with convolutional neural networks on image classification. There are no multi-level hierarchies, first of all. Second of all, the automatic hierarchical definition of sub-goals is somewhat inherent in the problem with mazes, but it's not so much inherent in other types of problems, and especially not in a general framework of given environment problems. It's not tested on a large scale. It's just tested on the small mazes, which is something that I'd really hope to see in research, like someone do. Please, like if you are into ML, test that. And also, like to use this over a wide range of tasks, not just solving mazes, we would probably need to find some way to encourage this separation of sub-goals, of sub-policies. So that's something that I'd like to see in future work and hopefully get to work on myself. The third challenge for AGI is learning to learn. Because, you know, today, people like me have to come up with things like that, which is a neural network architecture, or yeah, basically that. It's a neural network architecture. While we develop that fast, it's probably not perfect and definitely not instantaneous. So what we'd like to do is we would like to kind of replace people like me with an algorithm that does that. Building a learning algorithm on its own. So basically having an algorithm that learns to learn. That's, by the way, that image is from a very recent paper of a text-to-speech neural network. I think it's by Google. Yeah, it's WaveNet version 2, which is extremely useful, and that's what you heard at Google I/O, I think, like the whole thing that you heard talking, whatever. So, learning to learn, we would want to use different properties of the given task and problem, or even of the data, to build that algorithm dynamically for the problem. That would be a nice step forward, because you know, like artificial general intelligence doesn't mean fixed number of neurons, fixed neural network shape, but might also mean a neural network generating a neural network for this problem. Might also be good. We're not like fixed into one thing. So the neural architecture design should not be based on what I want to do, but it should be like automatically configured for a problem. And hyperparameters of neural networks should be tuned automatically, which this, for example, like there has been some work on this. For example, automated neural architecture design. Like that's the main point. We are not at zero. Which works. It designs, for example, for image recognition, it designs you a convolutional neural network architecture pretty well, but there are some problems. For example, first of all, it's not much tested on multi-aspect problems. It's just tested on very, very specific use cases. And it doesn't include non-standard operations, like this flowchart on there is a lot of non-standard things in there, and the algorithm wouldn't have figured that out probably. The fourth challenge is one that I find particularly funny, to be honest, because I've talked about how awesome deep learning is. But deep learning has weaknesses, and especially if you deploy deep learning in production, you should know about, like, especially the second one. The first is sample efficiency. You need a lot of data, you need a lot of trials to do anything. For supervised learning, you need large data sets with a lot of images and a lot of labels. That can be millions if you want to have like a really, really good system. Or you do transfer learning. For language data, you often need a lot, which is not a problem today in many use cases, but a large problem in other use cases, like, for example, medicine, where it's hard to get that because of privacy reasons, or many other use cases. For reinforcement learning, that same problem exists too, because interacting with an environment is not always cheap from a computational point of view or from a robot point of view. Imagine like your Go simulator is cheap. That's just moving a number in a 19 by 19 matrix. But a game like, for example, OpenAI tries to solve Dota 2, that's more expensive to interact with. Like getting the whole image, the whole screenshot of the screen, and inputting that to the neural network. We'd want to minimize the number of environment interactions we have. Because that sample efficiency is something that we humans have. If I look at an object once, I could probably recognize another instance of that object without ever seeing a second example of this, which is called one-shot learning. Some of you have probably heard that term. That's something we'd really like to see in deep learning. So that's a weakness. But a really dangerous weakness, especially for production problems that I want to raise awareness of, are adversarial attacks. Look, you see this image on the left, the panda bear? Well, it's obviously a panda bear. Our convolutional neural network thinks that this is a panda bear. Well, the certainty is not at 100%, but that's what it picked. Good. You see this like panda bear on the right? Well, that's not a panda bear anymore. Well, it actually is, right? So what is this? What we did there is, or not we, someone else did that. That's not my research I'm presenting here. What was done there is we formulated a new optimization problem. We said we want to maximize, given this image, given this neural network weights, without changing the weights, the likelihood of the class given. whatever that is, by the way. So what the task was basically is change the input image, let the network weights stay the same, and maximize the probability of gibbon. And the problem is that if you apply some special math that the image looks pretty similar than before, what you get is the image on the right, which you probably couldn't even distinguish because you add this noise-looking thingy with a multiplier of 0.007, and what you get is that. Sounds funny if I explained it like that, but imagine having that in an autonomous car. Because the big problem is, this doesn't only work with digital images. I could print this, and it would still work if I take a new picture of that, which is crazy, but I'm serious. It even works with 3D printed stuff. There has been an example from Google with that. So that's a big danger. That has to be fixed. And there is some research going into, a lot of research going into fixing this, specifically with extending your data set by randomly adjusting or making random changes to your inputs and training on that too. That helps, but it's still not completely solved. And that's a danger that's really, really important to have awareness of, especially in production. But that's also for AGI, that's completely no. So yeah, the ideas for future work in this case are very straightforward, just fix things. AGI challenge 5, that's a pretty interesting one, I think. Complex environments need complex policies. So if I want to be successful in a complex environment, I need to act with a very complex decision mechanism, or policy as we call it in reinforcement learning. That's true, right? But, well, how do we build complex policies? We need complex environments to build complex policies. So that's kind of the actual problem we have because, well, okay, policy, then be complex, I don't care. But now we have to create complex environments. And that's actually a problem that is, okay, of course, this explains itself. That's a problem that can be solved fairly easily. Using self-play, which basically is, self-play is a word for having an agent play against itself. For example, in DeepMind's GoBot, in AlphaGo, what they did is they let the program, or at least in version 2 of that, they let it play against itself millions of times, and by that it learned to beat itself over and over and exploit the opponent's strategy. And by having an AI be part of the environment, and think about it, if one agent interacts with an environment and an opponent AI, that AI is part of the environment for the agent. If we do that, we let the complexity create itself over the training time by having both agents improve and both agents compete. Having multi-agent competitive systems is actually the way to achieve complex policies. And there has been a lot of work done in self-play, and that's actually the leading approach in reinforcement learning right now because, well, that's just, it makes sense intuitively that leads to the best performing algorithms. So, because imitation learning is another interesting topic, imitation learning is when you basically learn from expert data. That's what the first version of AlphaGo did, to stay with that example. They downloaded professional Go games and learned from the policies that were played in these downloaded games, which always caps you at human performance. And as with the Turing-Test, we don't really want that. So that's the only way to get beyond human performance, because if you learn from humans, you're capped by humans. So that's the summary of the largely open problems in deep reinforcement learning. Abstraction, hierarchy. We should replace AI researchers with self-building algorithms, which is, well, funny to hear from an AI researcher, but that's what we're working towards. And deep neural networks are not perfect. They are great, really, but not perfect. How do we solve that? There are many possible approaches to this. For example, you could just handcraft algorithms like we have been doing, and maybe, well, some configuration that someone comes up with someday leads to AGI, which would be pretty amazing, is an option. Evolution of an algorithm, we evolved, so obviously that's an option. We could just evolve algorithms and see if that would work, see if that would lead to something that we could call AGI. We could also just completely throw away the whole gradient thing I talked about, the whole backpropagation algorithm that minimizes the difference between output and label, and maybe use something different. Maybe there is a different algorithm that just does a better job and that we haven't, or maybe have discovered or haven't discovered yet. Also an option. So, see, and another option is just having complete inspiration from psychology and neuroscience. Convolutional neural networks, for example, are inspired by our visual cortex, at least loosely. And maybe AGI has to be too. Maybe we just don't come up with it and have to look at our own brain. That's an option. So point is, there are a lot of possible pathways. And that's why, no matter, like, please don't listen to anyone telling you, like, in 10 years, we are going to have AGI. No, like, these pathways have completely different lengths. One might be, like, never reaching a goal, and the other one might be, like, if it's handcrafted deep reinforcement learning algorithm, that paper could be coming out tomorrow, could be coming out in 10 years, whatever. The point is it's unpredictable. Different pathways have different lengths in this case. And AI research, kind of business as usual, executes all of these paths, which is, well, probably a good strategy because you don't miss out. And it does so very fast. So, like, that's the other takeaway. Like, you don't have, we're not at zero, we're moving. And we're moving fast. And we're moving into all directions to explore different things. And there are, like, major improvements that were completely unsolvable a year ago, like, every day. If you read, like, archive.org, for example, if you're familiar with that, and if you look at the papers, like, it's just complete improvement every day. And there is another challenge that's not a scientific one. And that's ethics. That's something that everyone in this room has to deal with. And I guess I'm probably not the only one that has to deal with the other challenges, but this is one everyone has to deal with. First point is regulation. Regulating AI research from a government point of view is pretty difficult and unrealistic, to be honest, because there's just so much money in the industry. It's just not going to happen with lobbyism. Let's be realistic. So putting a stop on AI research because of potential dangers that there are, and, well, there are dangers because it's unknown, it's smarter than us, and it, well, like, maybe we introduce a bug, whatever. There are dangers. So, but having it stop is stupid because it also has potential upsides. It could solve problems that humans can't solve. Like, imagine you just make something twice as intelligent by putting another computer beside it. That doesn't work with programmers. You all know that. Like, but it would work with AGI, so why not? That would be good. So it has upsides. It can do so much for us. It can solve problems that we could never solve with our brains. And it doesn't even have to be completely detached from us. It could be an augmentation to our own brain to make us more capable of what we already do. So it has these upsides. Although these might seem scary to some, they're actually positive, in my opinion, at least. But it also has dangers and downsides. If AI, AGI especially, is used maliciously or exploited with things like adversarial attacks, that yields problems. That could yield big problems, honestly, because, you know, with atomic bombs, it's easier to defend against them than it is to attack with them. It's easier to build a rocket that, like, kills an atomic bomb that's coming into you than it is to have an atomic bomb come into you. But with AI, it might be easier to attack than to defend, which is a problem that's not solvable after you have encountered it, by definition. So it's important that we pay attention to safety while we research and while we work on improving this technology, and especially while we go towards artificial general intelligence. And that's something where I really want to give a very, very, very loving shout out to OpenAI. OpenAI's key policy, which, by the way, I don't work there, but I wish I would. OpenAI's key policy is always pay attention to safety, and if someone else gets close to developing AGI and they define that by more likely than a coin flip in the next 2 years, they will instantly stop researching and help them. That's what I call the best regulation you could have in a realistic manner. So yeah, that's that point. And the point that you have to deal with, not only think about but deal with automation not only coming into manual labor, but also into intellectual jobs, and especially with AGI that would just be basically gone instantly. There is a question that's also raised. External motivation goes away. There is no such thing as your salary bonus because you did a good job. There is no such thing as your boss saying, wow, that was great because the AI did it better. So what you'd have to do is you'd have to sort of find your pleasure and find your motivation intrinsically. You'd have to be able to define your own personal values. What do you want to achieve in and with life? And be able to say, well, I did a good job today reading my 2 books and going jogging for 5 kilometers. I'm happy and I am completely fulfilled with what I did today. So that would have to be an internal process. That's something many are scared of, and that's a question that's important to raise beforehand. But I think it's a beautiful question. And it's not only a beautiful question, it's a beautiful idea. Because you take the control over your own happiness and over your own fulfillment again. You take that back from external persons, and you also get out of this consumption society problem that we all have. Like, buying something doesn't make you happy, it makes, or at least people think, it impresses others. And that's gone too. So I think, honestly, automation of every single job gives you the time to do things that you really like to do. And if that's your job, you can still do it. Nobody forces you to not code. And you also take away the power out of other hands to control your happiness and your fulfillment. So that's, by the way, the reason why I personally think that moving towards AGI is a good thing. So yeah, that's the references I used. And if you have any questions or if you want to learn more, please use these sources. Very good sources, very easy to grasp. Oh, I like that everybody's taking pictures. Yes, go for it. Read all of that. Yeah. No, seriously. So if you're more advanced already, Archive Sanity's, actually there was a talk about an advanced project, Keep Current today, that tries to substitute for Archive Sanity. But Archive Sanity is a way to organize machine learning papers so you find what you want to find and you can read what you want to read. The RL Bootcamp is something that I think is I would call it the best course on reinforcement learning out there ever. It's something it's made by UC Berkeley from leading researchers, explained for probably a kind of an open audience, not really, but it's pretty advanced. But you'll get the state-of-the-art algorithms, or some of them at least, if you watch this whole course. And of course, the blog posts and things like that augment this. And yeah, have fun watching this and have fun reading it. So if you have any questions, please fire them at me. By the way, we still have this room. It's empty now, so we can stay here for the questions, if anybody has one. I mean, would actually surprise me if not. Are we not? Somebody told me. I was told that this room is empty afterwards.
Just read the first one. Is there any...
Oh, we have sex. Oh, wait, that's the question. I'm stupid, sorry.
Yeah.
No, seriously, if you do too much research, you get stupid in the basic things. Trust me. Seriously. Seriously, ask my girlfriend, seriously. So, is there any potential risk for humanity as described by Elon Musk by building master algorithm? Yes. Yes. But the point is, yes, there is risk, but that's not a reason to not do it. Humans have been exploring forever. Evolution is a key principle of the whole universe, and moving forward might involve some risks. Humanity has taken insane risks in the past, and they have all paid off, or at least for us, maybe parallel universes have died out, but for us they've paid off so far. And I think, honestly, if we pay attention to safe AI research, is the right thing to do. If we have a competitive race of who arrives at AGI first, that's a problem. And that's something we should all try to avoid, especially if you have some kind of connection to AI research departments. Tell them that. That's a bad thing. Don't have a race. Okay, so what's the next one I should answer? Could an AI learn to program, do the job of a dev, and basically develop AIs? Developing AIs is one of the first very advanced jobs that's going to be automated, I think. That's the learning to learn part. So you guys are going to work longer than I do, than I will. So which means I get to retire earlier, which is pretty nice. No, just kidding, I love work. But would it be able to do the job of a dev? Yes, as soon as you have an AI, yeah, well, AGI, yes, that's the definition of it. So if it ever will, well, that's the thing with the pathways. I don't know where the path to AGI lies and how long it will take. But if we ever have AGI, it by definition codes better than all of you. By definition. So sort of has to. Why do we need artificial general intelligence? That's a question. There are some people, back then when cars were invented, that still wanted to ride their horses. Do you like riding horses on the streets of Vienna? Do you? Okay, 1 versus 600. Okay, so why do we need artificial general intelligence? Because we have major problems as humanity, as a whole species. We have the problem of conserving our own planet. We're completely ruining this place. We have the problem of scientific advancements, which happen and happen faster every day, but they could be even faster, which, well, this might be the next step towards it. We have things like cancer, which for a system that thinks super fast and super great might be easy to solve, while it's not for us. We can't remember all the molecular, I'm not a biologist, I have no idea, but all the molecular thingies, maybe AGI can. That's the definition, it's smarter than me. So, well, it just solves the problems that we can't solve. And we have a lot of these problems as society. And like just living every day and thinking, well, the world still turns around. Yes, for you, but look at other continents. The world doesn't just turn around for them. And it probably won't just turn around for us if we continue like destroying our planet like we do now. And well, things are improving, but they could be improving faster and they could be improving better. That's why we need it. Can I dodge the next one? I don't like singularity topics. Like, are you scared of your own findings at all? The reason why I want to participate in this research and why I'd like to do this public speaking thingy, and will love to do that in the future, is to raise awareness of the dangers. Am I scared? Well, I'm careful, I guess. I like to say I'm careful. The expected value, kind of doing this research is positive, because I think humanity will benefit, but we have to pay attention. So scared? Well, I'm not scared of my own findings. I'd rather be scared of other people's findings that don't care about safety. That's what I'd be more scared of. Which is also why I'm 19 and already like here, because I'm really like scared that other people like do stupid things. So I'd rather like participate in a team that's not doing stupid things. Like OpenAI. Like OpenAI is great. Great. Intelligence is just one of the human. We're not trying to build humans. We're not trying to substitute you as a person. Like that's the whole thing. What we're trying to do is to make you not have to work and to make something that exists better in solving problems than you are. You're not going to be replaced. Like, you're still having your human social interactions, you're still going to conferences like this, you'll still have your coding projects, you'll still have your GitHub, like, we're not replacing you, so that's just one thing I want to note. So, but will they be able to experience and feel emotions? I'm not a neuroscientist, and I have no idea how I would, like, this is not something that I know, this is something that I think, like, just important. I think you could describe pretty much every process that happens as something that happens with numbers, some formula, kind of. Even if it's a complicated one. Like neurons firing are pretty simple, or not pretty simple, but far simpler than emotions probably. Like again, I'm not a neuroscientist, me don't know, but probably we could model emotions, but I don't know, like that. It's probably much better to, like, if you want empathic AI, if you want AI to be able to like re-feel what you feel and predict what you feel, it's probably much better to approximate your emotions rationally rather than have it feel itself, I think. Because in decision making, rationality is always better, but if you want to consider emotions, you should do it rationally, like speaking from a rational point of view. What are you thinking about the stop button problem? The stop button problem is kind of solved. That's called reverse reinforcement learning. Instead of just having your specified goal and doing everything to, oh, by the way, for the people that don't know what the stop button problem is, imagine you have a robot that walks like from here to there, and its job is to bring me this thing that is on the ground down there, but there is whatever, like there's a hole in the, no, not a hole, like, okay, no, there's a hole in the bottom, in the floor, and I like that robot, it's expensive. So what I want to do is I want to press that button when I see it's walking towards that hole. What does the robot do? It comes to me and like kills me, because if I press the button, it's not able to get its reward from bringing this back to me. That's the stop button problem, basically. That's kind of solved, because if you initialize the reward not as bring me the bag, but as make me not press the stop button, you solve that, kind of. Like that's sort of a rough definition of the inverse reinforcement learning problem.
Eric, time is over now for this room. For everyone who has to go to another stage or somewhere else, please give once more an applause for Eric. Thank you very much.